All right, so let's start the second day's lecture with Aristomenis Donos, who will talk about applications to condensed matter.
Can you hear me? Yes, I can hear me. Okay. So I guess in this series of lectures, I'm going to talk about applications of holography in condensed matter systems. And to make worth following this, I think I need to give you some motivation for doing that. So let me give the quick title. So that's ADS, condensed matter theory. And I guess that Horatio convinced you that holography is a very good framework, a very nice framework to study strongly coupled systems. And strongly coupled condensed matter systems do exist, and this is what we would like to study. However, we are particularly interested in special classes of condensed matter systems. So it is condensed matter systems which have some sort of scale invariance. And this is in the relativistic case where CFTs are coming in. And scale invariance is important for systems close to criticality, or maybe systems at criticality. Okay, you have seen this probably if you have done statistical mechanics or statistical physics and have looked at phase transitions. You might know that at finite temperature, when you are exactly at the critical temperature, then there is some emergent scaling invariance. There is what is called the correlation length in the system. The correlation length goes to infinity as you approach the critical temperature. So any other length scale in the system gets washed out, and you suddenly get scale invariance in the system. So from something similar happens from the zero temperature point of view. So let's stick on this axis if this is temperature, and this is some sort of coupling in the system G. Let me stick at exactly zero temperature, and let's say that as I'm varying this coupling, or some constant in your system, there is a critical value for this coupling constant, under which you go from one phase of the system to another. For example, you could have a system which is an insulator for small coupling, and these systems usually become superconductors or superfluids as you increase the value of this coupling. So right exactly at this critical value, where it is exactly the critical point, the system exhibits scale invariance. Okay? And I will tell you more precisely what I mean by that. So if you are looking at a dynamical question, for example, you compute the two-point function of some operator, then let's say that your operator is psi, and you compute the retarded Green's functions of this operator. And if you have a function of frequency and wave vector k, and you see that I'm splitting omega and k because I'm planning to look at non-relativistic systems. So it's not like everything is packaged under a single four vector. So scale invariance will tell you that this retarded Green's function will scale with the amplitude of the wave vector. There will be some number eta, and then some function, which is only a function of the ratio of omega, the frequency, to some power 1 over z. This is z, it's not 2. And what is hiding behind this relation is it tells you basically that. And this eta is related to the dimension of the operator psi according to this. So if you are in d dimensions, which includes time, then the dimension of the operator psi will be d minus 3 plus z plus eta. So what hides in this scale invariance for the Green's function is that it tells you that there is a secret scaling of space-time, if I go to coordinate space, which is telling you that the spatial coordinates want to scale with lambda, some parameter, but time will want to scale with the same parameter to the power z times t. Okay, and this z is what we call the dynamical critical exponent. Okay? Good, so exactly at criticality, correlation functions start scaling according to this formula. And you have an emergent number, which is the dynamical critical exponent. Now, if it so happens that your critical point at GC has an emergent relativistic symmetry, if you have Lorentz boosts, for example, so relativistic symmetry tells you that Z has to be equal to 1. So time and space would have to scale in exactly the same way, and Z can only be 1 for the relativistic case. Moreover, relativistic symmetry will completely fix this two-point function. Right, so if you have relativistic invariance, then you know that the only way, and you are at 0 temperature, then you know that the only way that this thing can depend on omega and k is through some Lorentz invariant combination. So it will be some function of minus omega squared plus k squared, and this will be proportional to minus omega squared plus k squared to delta to the power of minus d over 2. Okay, so scale invariance plus relativistic invariance will basically tell you what this two-point function will have to end up being. Okay? If you don't have relativistic invariance, then this is all you can say, without, I mean, just by symmetry, okay, without knowing any of the details. And indeed, yes? Delta psi is the dimension of the observable psi, is the scaling dimension. Okay? So if I scale omega and k by lambda, you can see that this scales so from here you can see that g of lambda omega k, and I have to scale lambda with power z. This scales like lambda to the minus 2 plus eta g of omega comma k. So this is what this achieves. Where is the z dependent? Well, you see, to cancel out lambda from here, I have to take omega to be lambda z times omega. So if I plug in lambda z, the power omega here, lambda will cancel out with the lambda k here. Yes. It's omega to the power 1 over z. Okay, good. Yes? That's in the coordinate space, right? That's in Fourier space. I'm a condensed matter person. I like omega and k. Yes. Well, can you, yes, I think we need a microphone. Yeah. Yes. I think I need to hear the question again.
Hello.
Yeah.
Yeah. So basically, in CFT,
Yeah.
what I have read that these x and t, that is something like x mu is scale as some lambda x mu. So basically, lambda is the same for all mu's. So
Exactly.
so basically, you are saying that is space-time scaling is x going to lambda x and t goes to lambda to the power something times t. So why is the different scaling goes for t and x?
So this is, okay. For a relativistic CFT, yes, t and x have to say in exactly the same way. But there is fixed points or critical points which are not relativistic. Okay, I mean, from the RG point of view, I still want things to scale somehow because my RG flow has to stop somewhere. But if I'm not flowing to a relativistic fixed point with a relativistic symmetry, then they cannot scale in the same way. But the RG argument tells you that you need scaling symmetry. Exactly. Exactly.
Yeah, so condensed matter systems, non-relativistics, right?
Exactly. Yes. I want to consider both, and there is a very good reason for that. I hope that I will make this clear in my lectures. So, from the technical holographic point of view, I know how to deal with relativistic CFTs. That's what I understand from the microscopic point of view. And then I want to take these theories, deform them, add finite chemical potential, introduce scales, lattices, whatever you can imagine. And then this thing will have to flow somewhere in the low energy limit. And then the low energy limit will be precisely this z not equals 1 cases. Okay, so there will be some high energy theory which will be a relativistic CFT. I need some UV fixed point. And then I will take this UV fixed point, deform it, and then try to hit the non-relativistic fixed point. It is an appeal to universality classes of fixed points. Okay, I mean, we will do this step by step. I'm just telling you now the quick story, but I will try to make this as clear as possible. Okay, so good. So what are examples of condensed matter systems? Because condensed matter systems include relativistic fixed points. The speed of light will not be 1. It will be some parameter set by other parameters of the system, but there will still be a speed of light, okay, which is not c. It is some typical fermion fluid velocity, velocity in the system. So one example of a relativistic system is graphene at 0 chemical potential. So in this case, you have fermions moving on a honeycomb lattice, and there is a valence band. Normally, the valence band and the conductance band, I mean, if this is one axis, the horizontal axis is k, and here you have energies, the valence band and the conductance band will have some curvature if your fermions have an effective mass. When you have a honeycomb lattice, what happens is that the valence band and the conductance band become a Dirac point. So they become kind of singular, and they even touch. So here you would have your chemical potential. The chemical potential is exactly between the valence band and the conductance band. So effectively, what you're getting is massless fermions. Okay, so massless fermions into +1 dimensions, you will get a conformal field theory, a scale invariant theory. And the velocity, the speed of light will not be the usual speed of light. Another example is if you take bosons and you put them on a lattice, then this parameter G is basically the parameter that tunes the repulsion between the bosons and the amplitude that they have in hopping from one lattice side to the other. If you make the repulsion very strong, you will get an insulator. The bosons will not want to live on the same lattice side. If you make the repulsion very, very small, you will basically have free bosons, okay? And in going between the insulating phase to the free bosons case, and you know that if you have free bosons at low temperatures, you will have Bose-Einstein condensation, you will have a superfluid. So that's basically the insulator superfluid phase transition that I talked about here. And those will have a relativistic symmetry as well. Okay, that will also be a Z equals 1 story. Now, so this is basically the insulator superfluid transition. Another case is fermions on a lattice. Massless fermions on a lattice. So this is basically just like graphene, but then at each lattice site, those fermions are interacting with an order parameter, which is the antiferromagnetic order parameter. Okay, so these are all examples which have Z equals 1. Now, yes?
By relativistic, you always mean that the HK relation is linear, or you just mean Z is equal to 1, or are both the same things?
Z equals to 1 with necessarily the speed of light not being equal to the usual speed of light.
Yeah, but the EK relation would still be linear?
The EK relation would still be linear. The constant of proportionality
will be different.
Will be something else. Okay? Now, good. Now, I want to tell you about an example which has Z greater than 1. And you might expect, so all these examples have 0 chemical potential. Okay, so there is no net charge density in the system. So at finite chemical potential, there is a chance that you will, because the chemical potential itself breaks Lorentz invariance, there is a chance that you will actually break, that you will flow to something that doesn't have Z equals to 1. So Z would be greater than 1. So an example of that is semiconductors. With touching valence and conduction bands. Okay, so this is very similar to graphene, but the valence and the conducting bands have some curvature. Chemical potential is exactly between the valence and the conduction bands. And this leads to Z equals 2. Basically, you can say that you can think of it as, energy goes like p squared. These are really non-relativistic fermions, so that will end up having Z equals 2. Okay, this is all at 0 temperature. Why you might want to consider 0 temperature configurations in the holographic context. Equally intriguing is finite temperature. Okay, so this is all why 0 temperature is interesting, but at finite temperature, there is still questions that haven't been fully answered. Now, at finite temperature, if you are not at too low temperatures, things are more universal. Okay, so there is a temperature which kind of separates you from whatever the ground state of the system is. And what the ground state will be, as long as your temperature is not too low, you will have more universal physics, I mean, away from these critical points. You can ask questions which are quite universal and general, I mean, independently of all that. What are these questions, and why are you interested from the condensed matter theory point of view? So I'm looking at strongly coupled systems, and so at strong coupling, there is often no quasi-particles. So a quasi-particle would be some excitation in your system that has a very long lifetime. It could basically appear as if it is interacting very weakly with the other quasi-particles in the system. So I could basically take that. It could have some mass, some lifetime, some very long lifetime, and basically start building a free theory around this quasi-particle. So even though the system would be interacting, then I can start building an effective theory by using these excitations, which would be equally good for the questions that I want to ask. However, when you are at strong coupling, and from a holographic point of view at infinite coupling, there is no such excitation. Okay, so the thing looks basically like a soup, which doesn't have any particles in it. Okay, so the excitations are just dying off immediately. However, if you are a condensed matter person, what you are mostly interested in is large distances. So at large distances, there is something universal happening. So at large distances, physics for these systems is dominated by the following. It will be dominated by conserved quantities. What do I mean by that? So let's say that energy is conserved in your system. Okay, I can think of increasing slightly the energy, you know, in a global sense, everywhere, at every point in space-time the same. And if I increase the energy density of the system everywhere uniformly, that's not going to change anything. Okay, and this increase will be there forever. It will never decay. However, if I make this increase, you know, with very long wavelength disturbances, I mean wiggles, then I know that somehow the system will have to reach thermodynamic equilibrium, and these wiggles will go away. And the wiggles, I mean, the longer the wavelengths of the wiggles, the longer it will take for the system to go back to thermodynamic equilibrium. Well, that's a quantity that looks like a quasi-particle. Okay, so at long wavelengths, and I said energy, it could be charge density, it could be any conserved quantity. Okay, so at long wavelengths, conserved quantities, in the way that I just described, they dominate the dynamics of the system. Or the equilibration of the system, yes?
Yeah, okay. So you gave a list of examples of system which has z equals 1, z equals 2. Is there any way I can see directly that the symmetry should be enhanced for the systems on the left? Or is that just an observation that you make?
Well, there is effective theories that you can write down, and they have relativistic symmetry built in.
So for instance, graphene at 0 chemical potential, how do I see that
Oh,
it has an extra
I
symmetry?
tried to argue based on this. So here, I mean, this is energy as a function of k. Okay, so if I write energy proportional to k, that's already a massless relativistic particle, isn't it? Yeah. So for a relativistic particle, you would have energy squared is p squared plus m squared. C is 1, of course. Okay, if I have something massless, then E is proportional to P. And this is what happens. This is the dispersion relation that you will get for fermions. This is called the Dirac point. It is the honeycomb lattice plays a significant role in getting this dispersion relation. So that is a system with Z equals 1.
Okay. Yeah.
Okay?
Thank you.
Good. Okay, so if I go back here at long wavelengths, what else can dominate physics at long wavelengths? Well, the other thing is, you know, symmetry breaking in condensed matter systems is common ground. I hope that we will reach the point where we will talk about symmetry breaking in holography, but, you know, basically, the free energy of the system is a function. You can think of it as a function of the modulus of some order parameter psi squared. And if it is a function, if there is this U1 symmetry where you rotate psi, I mean the order parameter in the complex plane, and it doesn't cost you any energy to increase, I mean, to change the value of the angle, then the value of the angle, as long as you are in the broken phase and psi is not 0, then the angle of the system plays a very similar role to a conserved quantity. So if I change the phase everywhere in my sample, the same way, nothing is going to push it back to the old value. So it will be like a conserved quantity. However, if I start changing the phase, you know, in a manner that varies with space, and the wavelengths of this variation are very long, then it will want to equilibrate again to some constant phase everywhere. That will be a slow mode. And this is why I want to say that Goldstone modes, this is a Goldstone mode, what I just described. So Goldstone modes will dominate also physics at long wavelengths. More generally, I want to say that almost conserved quantities will also dictate what happens at long wavelengths. What is an almost conserved quantity? You know, if I had electrons in empty space and I just gave them a kick, I would give them some momentum, they would keep traveling with the same momentum. Nobody would stop them. However, in a condensed matter system, I know that I have a lattice. Okay, there is all these atoms, annoying atoms that stop the electrons from running. And this is what actually breaks translations in this system. So by breaking translations, you know, momentum is no longer conserved, but it is almost conserved. It decays very, very, very slowly in the system. And this very, very slowly in the system means that there is some, you know, these quasi-particles that we were talking about, they have a decay rate, which is, I mean, momentum would have a decay rate in the system, but it would be very slow. So it could still be a player in the dynamics of whatever is going on. So almost conserved quantities is another player. Okay, so far no holography, right? There is no need for holography. However, you could tell me, yeah, okay, good. Then write down such theories. That could be writing down effective theories of hydrodynamics, but there is a catch. Okay, condensed matter systems have very small symmetry. They have very little symmetry. Okay, and I mean, you know how to write down, probably, many of you might know how to write down relativistic hydrodynamics. That has a lot of symmetry. It has Lorentz symmetry. You know exactly what you are after. For a system which, I don't know, breaks translations, there is a few Goldstone modes. You might be close to a phase transition and there is other stuff going on in your system. It is very hard to come up with an effective theory. However, holography can model all that somehow, and you can actually use holography to extract effective theories which capture precisely this scenario over here. So what are the reasons why you have little symmetry? Well, the underlying lattice structure breaks translations. And there is also order parameters in the system which break translations spontaneously. Okay. So let's say that you have used holography, you have built this effective theory. So what would you want to ask? What is the experiment you want to carry out in holography? Okay, there is the ground states. And of course, if your system has all this stuff going on at the same time, I mean, you have symmetry breaking, you have broken translations, you can imagine that then you ask the more ambitious question, what are the ground states of the system? That becomes an even more difficult task. Holography is, again, a framework where you can go and ask these questions. Even in that context, it can be difficult, quite difficult, but at least you are solving some classical system, you know, it's much more tractable. Whether you can trust what you find, that's a discussion we might want to have. Okay. So what you might want, so if you have this theory of, let's say, hydrodynamics or long wavelength excitations, you can ask the question of transport in the system, which is a much simpler question than discussing the full long wavelength dynamics. So what is transport? So let's say that you introduce to your system some external electric field E and some temperature gradient. You know, you take the temperature and you make it vary in space, and you know that this will kick off heat currents, electric currents. You will get some measurable quantities. So you want to find the response of your system, which is the electric current J as a function of frequency, and the heat current of your system, which is, again, a function of your frequency. Now, if I write the sources, which is the electric field, and it depends on frequency, and the gradient of temperature, which is now an external source, then if I write them in this matrix form, the response, then these coefficients are what is called conductivities. Okay, and I want to extract this conductivity matrix. Okay, so sigma is basically like Ohm's law. You know that if I introduce an electric field, there will be some electric current. The constant of proportionality is what you could call electric conductivity. And there will also be a heat current, right? So this alpha bar will tell you how much you're exciting the heat current in your system with an external electric field. So alpha bar and alpha in a time reversal symmetric theory will have to be the same number. And there is an argument for that based on Green's functions. Kappa bar is the thermal conductivity of the system. You introduce an external temperature gradient, you get some heat current as a response. The coefficient kappa bar is the thermal conductivity. Now, I want to tell you a few things that are more traditionally assumed in condensed matter physics, and they don't happen, both in reality and in holography. So if you have this quasi-particle picture, which doesn't exist, for holography at least, if you have this quasi-particle picture, then the mechanism that gives the electric current and the heat current is very similar. Okay, so what is this mechanism? So you can say that the current will be some charge density that you have in the system times the velocity of your particles in the system. Makes sense? That's what they told me in high school. It was okay. And then the heat current will be like something like the entropy density times the same velocity. So you have these particles, they move with some velocity, and all the transport into your system is happening precisely because of that velocity. Okay, this is the assumption behind this. However, if you take the ratio of these two numbers, well, division in some sense, then you will find that this velocity drops out, right? So you find what is called the Wiedemann-Franz law. So if I mean, this will be a number which is independent of temperature. And you know, in strongly coupled systems like cuprate superconductors, you don't see this. Okay, this constant of proportionality is a very non-trivial thing. If you compute, for example, the DC conductivity, which is the omega goes to 0 limit of these things, and you plot this ratio as a function of temperature, it's not a constant. If you follow this quasi-particle picture, you should find a constant, which is independent of temperature. Well, it is not a constant, even in real condensed matter systems. So there is other mechanisms which are different from this for heat and electric charge transport, and holography knows about it, which is a good thing. We will see. I mean, that's the plan, right? I will show you how these things work. But now I want to tell you the motivation. What else do I want to tell you? So holographic theories basically fall in this universality class of theories which don't have quasi-particles. We can ask and learn new physics, I mean, not captured by this. And it is a very interesting thing to look at. So you can use holography. I hope I have convinced you that it makes sense to use holography from two slightly different points of view. So the first one is the statics. Okay, I talked about ground states. I talked about phase transitions. So, you know, looking at static configurations in holography will give me new ground states. And we will have a look at that. Another thing that I didn't discuss too much here, but I hope to discuss in the lectures, is symmetry breaking. Okay, it's configurations in holographic theories which have to do both with phase transitions and spontaneous symmetry breaking. And then there is also, you know, this question about the lattice which breaks translations and it relaxes momentum. That has to do with explicit symmetry breaking. So I can do a bit of both in holography. It is sources that I can put there by hand, which break the symmetries, and I can see the effect that they have on the system. And there is also the real-time dynamics. So I would like to use holography to derive effective theories and hydrodynamics. And then if I am, you know, if I want to compare to some experiments, I can take these effective theories and I can study transport of heat and charge. Okay? Now, what are we going to do here? I mean, you can do many things with this, right? But I want to tell you sort of coherent story. I don't want to confuse you with many, many different things. I will try to keep it as simple as possible. Well, I mean, you know, you can suspect that since I'm looking configurations with very little symmetry, numerics, hardcore numerics is probably part of the story. I have contributed to global warming myself, a lot of electric current and heat produced, bad for the planet. We will avoid numerics. I just want to tell you, okay, so what? You have some solution, what does it mean, okay? Okay, outline. So we are going to start with the basics of, I want to call it Z equals 1 holography. I mean, no disrespect for Horatio. I know you did that last week, but there is certain aspects of that that I want to stress, and they will be very useful for what I want to tell you, okay? Then we are going to discuss these fixed points with Z greater than 1 as disconnected entities, as solutions on their own, okay? And then we are going to glue these fixed points with the more serious stuff of Z equals 1 holography, and I want to discuss RG flows in the context of holography. So this will basically be deformations, nonlinear deformations of the UV CFT. And I also want to include chemical potential. Then we will talk about thermodynamics and black holes. You have seen black holes. Probably they appear in every single lecture that you will see this week and last week. But I want to get something out of black holes, okay? I want to extract something from them, something useful. Something that I find useful in this context. There is many useful things about black holes. So I want to stress what these useful quantities are, because they will give me something nice for later. So then we are going to discuss linear response and quasi-normal modes of black holes. And that will take us naturally to hydrodynamics and we will talk about Kubo formulae. And what else? And holographic transport coefficients. So we will build a very simple theory of transport. I will do the simplest thing possible that you can do in holography. And this is charge diffusion. So first I will describe what diffusion is from the hydrodynamics point of view, and then we will just follow the steps of hydrodynamics and build an effective theory from holography. And if there is time, I hope there is time, we are going to talk about phase transitions and superfluids. Okay, so I think it's a very modest set of things we can look at in ADS CMT. I hope you will get something out of it. Okay? Good. Yes?
Computations in ADS to get these things, or
okay, so where is gravity going to be, right?
Yeah, means
so that will have gravity. There will be lots of gravity here. We will find we will write the gravitational solutions that you need to describe this Z greater than 1 systems. RG flows, yes, they will be in the context of gravity. We will flow from one fixed point to another fixed point, and we will see how to do that. Thermodynamics, I mean black holes. Okay, there will be gravity. Linear response, well, that's more like a quantum mechanics question. And we will see, okay, you can compute Green's functions from gravity. The Green's functions that you get from black holes have a very specific form. This is how much gravity will be there. Hydrodynamics will have nothing to do with gravity, but even up to here. And then we will go back to gravity and see how we can build a hydrodynamic theory from black holes. Okay? And phase transitions will be gravitational. Any more questions about the agenda? No? Okay. So, yes.
But like more philosophical question. So in like usually we say ADS CFT in the high energy case is not like it's at a conjecture level.
Mm-hmm.
But here we have actual systems where you could test those predictions, right?
Mm-hmm.
So, and are there like experiments done that verify this correspondence, or it's still at a more formal level?
It depends on what you want to learn from holography. If you want to find a theory which has the correct power in temperature with all the coefficients fixed, that's not my style. It's a matter of style. That's not what I want to extract from it. What I want to extract from it is, generalities about, for example, these effective theories. These effective theories had been, I don't know, there is papers from the 60s and the 70s which are trying to look at these questions. Very good papers, but have they done it all? Have they missed something? Okay, and these theories were not written in a derivational sense from a microscopic theory. Mm-hmm. It was general expectations, starting from thermodynamics and then generalizing to hydrodynamics. But it turns out that some cases they have missed things. Okay. So, and we have learned about this from holography.
I see, okay.
Okay? So I think this is what I want to extract from it. You can look at phase transitions, for example, but if you just look at the classical limit of holography, you are throwing away any thermal fluctuations. And you know that if you are very close to phase transition and you just ignore thermal fluctuations, you will get something wrong. Thermal fluctuations will dominate everything close to the critical point. But when people start writing these effective theories, I'm thinking of Hohenberg and Halperin, for example, you start with the assumption that you know what you're doing, you ignore all these thermal fluctuations, then you start renormalizing, you see that they dominate everything, and you reach the critical point by starting and writing something which is very classical in the beginning. But have they written the correct thing down? Any more questions? No. Okay, right. So I want to say very few things about CFTs in general, no gravity yet. Okay, now we are in the Z equals 1 regime. You can think of them as, indeed, the Z equals 1 fixed points. You can think of them as the UV theory that I want to deform. So let's see what we can say about them. So relativistic QFTs are basically invariant under the Poincaré group. Okay. So what's this transformation like? So you would have translations. I can take x mu, and I can shift it. There will be a shift vector a mu, or I can do a Lorentz boost with Lorentz transformations given by the matrices lambda. So let me call this equation 1. And what do we know? We know that this lambda belongs to the group SO 1D minus 1. And the algebra is, I mean, if I look at infinitesimal transformations and I look at the algebra, I will have the generators of the Lorentz group, which I call M. And I will also have the generators of translations, which we usually call P mu. Okay. You know, these generators will basically close some algebra. I might not want to write this down. I don't want to spend too much time on this. And what? The point is that these transformations one are isometries of Minkowski spacetime. Right, so if I use Cartesian coordinates, then you know that if you write the metric ds squared is eta nu nu dx mu dx nu, then you know that this metric is invariant under these transformations. In fact, this is how you find this metric. You want your theory to be invariant under this. The quantity that is invariant under this is the Minkowski metric. Okay? Good. Now, for a theory which flows, which is exactly at the fixed point, you want to have additional symmetries. That's not enough. So the more general class of transformations include dilatations, so you can basically scale your coordinates by some parameter lambda. This is basically the scaling that I was discussing earlier, but with z equals 1. Okay? So you know you want to have dilatations. And the generator of dilatations D acts on functions, on a function f, as I x mu partial mu f. I mean, you can derive this just by that, but just by doing that. Okay, now there is, I mean, if you, under a minimal set of assumptions, under a small set of assumptions, this is all you could ask from a relativistic theory, to float a fixed point. However, you do get some extra transformations, I mean, some extra symmetries in your theory, which are called the special conformal transformations. So basically, you take x mu, and you change that to x mu primed. You have x mu plus some parameter, some vector parameter b mu, x squared, divided by 1 plus 2 x mu b mu, plus, I think, b squared x squared. Okay, and these are the special conformal transformations. However, these transformations, these coordinate transformations, are not anymore a symmetry of the Minkowski metric. Okay, they do not leave it invariant. So these are going to transform the metric non-trivially So if ds squared is your original metric, the new metric you will get will be some scalar function, omega. This is my omega, okay? I know you are used to probably a different capital omega, but that's my omega. That's how my mother showed it to me. Okay? So there will be some function which will multiply your old metric. And for dilatations, this omega is just lambda squared. I mean, you can check this, just do the transformation, you will find what I'm saying. It's not magic. For special conformal transformations, this factor omega will be slightly more naughty. It will be 1 minus 2 b mu x mu plus b squared x squared. Okay? So this is obviously not a symmetry of Minkowski space. However, it should give you a symmetry of your theory. And the way for, I mean, what should happen in order to be a symmetry of your theory, it means that the fields that participate in your theory will have to transform in a specific way under these transformations. Okay, so the first thing to notice is, yes, okay, it's not a symmetry of Minkowski space, but together with the Poincaré group, they close a nice algebra. These commutators I want to write. So if D is the generator of dilatations and K mu, you see the special conformal transformations have a vector as a parameter, right? So for each component of this parameter, you should have a generator. So there will be a vector of generators. Let's call these generators K mu. And you can check that the commutator of dilatation, of the generator of dilatations with the generator of special conformal transformations will give you I K mu. The commutator of the Lorentz transformations, the Lorentz generators, Lorentz group generators with D is going to give you 0. And I want to write here, what else? The commutator of the generator of translations with the generator of dilatations, which is going to give me an I P mu. Maybe it is worth writing down the other ones. Well, I mean, it will just demonstrate that it closes some algebra. But what I want to keep from this discussion is something slightly different. So you will have an eta alpha mu, k beta, minus eta beta mu, k mu. Sorry, k alpha. What else do I need to write? Oh, the commutator between P and K. We'll have 2I M alpha beta minus 2 I eta alpha beta D. Okay. Now, the generic QFT, of course, is not going to be invariant under these transformations. You need to have already gone to a fixed point. So the special class of field theories that are invariant under this group are, of course, the conformal field theories. Now, something to notice is the following. So for quantum fields, let's say a scalar field phi, the transformation of phi, let's call it phi primed, under dilatations is not going to be just a change of coordinates, right? So if I was just transforming phi as a scalar, I wouldn't need this at all. But I'm telling you that I'm going to transform it in a way that will leave your theory invariant. And the way to do this is by introducing lambda to the power delta. And delta is called the conformal dimension. Now, at the level of commutators, I mean, if you want to see what D does to the field phi, well, you know the full transformation, but just from this transformation, you can write that the commutator, D, that's the generator of dilatations. Okay, so if you want to find what K mu does, expand this at linear order in B mu, and that will give you the generator K mu. Okay? So D is promoted some operator, and then the commutator of D with phi is going to give you I, then delta plus x mu partial mu phi. So you see that, for just a function, when I'm just doing coordinate transformations, this part of the operator is here, but for a quantum field that I want my theory to be invariant under these transformations, I need this extra delta here. Okay? So what is this telling me? So if I set x equals 0 and I look just how D acts on phi at the origin, so at the origin, commutator of D with phi is going to be I delta times phi at the origin. Yes?
Should there be a x prime as well in the transformation rule, or phi prime x prime?
Over here? Over here? Oh, I'm just defining, yes, the new field. It is the field phi primed defined at the point x. Right? Okay. Good. So this commutator is telling you that if I'm thinking of representations of this algebra, then this delta is probably one of the good quantum numbers. Okay? It's like the third component of angular momentum when you're looking at SU2. Okay, now why did I write this? So if I look at this and that equation, right, they look like lowering and raising operators for the conformal dimension delta. In fact, these two equations are telling me that P mu acts as a lowering operator So if I act with P mu on phi, and then I check what the commutator of D with P mu phi is, I will find a delta minus 1 here. This is what this means. K mu acts as a raising operator. Now, this starts smelling more like SU2, okay? But you know that, I mean, unitarity in SU2, if you want to have normalizable states, there has to be a maximum value of the third component of angular momentum and the minimum value for the third component of the angular momentum. For the conformal group, unitarity requires a minimum value of delta. Okay, so there is some point where you keep acting with P mu, P mu, P mu, and I mean, after a certain point, you should find 0. I mean, just a state annihilated by P mu. So this lower bound, moreover, unitarity requires that this lower bound in this representation will have delta greater or equal to d minus 2 over 2 for scalar operators. Delta will be greater or equal to d minus 1 over 2 for vector operators. And if you have a spin S operator, then delta should be greater or equal to d plus S minus 2. Sorry, this was not vector, this was 1/2 for spin 1/2 operators. For spin S operators, you should have delta greater or equal than d plus S minus 2 for spin greater or equal to 1. Okay? Yes? P and K. Oh, yes. Yeah. What do I have? Yes. Sorry. Thanks. Okay, good. So this will play an important role, especially if we get to the point, I want to get to the point, where we discuss phase transitions. Okay, this unitarity bounds, stability. I mean, you see them from the CFT point of view. I mean, the same bounds exist from the gravitational point of view. Okay. So, as you might have seen, I mean, this symmetry completely fixes the form of 2-point functions, the form of 3-point functions. That's all you need in the theory to fix the form of these correlators. Now, to get to the point of looking at holographic theories, there is an important observation on how to realize this more geometrically. You see, this symmetry group, it was not, I mean, from the field theory point of view, this was not a symmetry of the space-time, okay? It is a symmetry of the theory, but your space-time, which is Minkowski space, actually transforms non-trivially under these transformations, okay? From the holographic point of view, if we want to realize all that, we want to realize it in a geometric way, okay? So we should kind of find some space-time where this is actually a symmetry, okay? It leaves the background of whatever we look at invariant. Much like the Lorentz group is a symmetry of Minkowski space-time. We want to find the space which is invariant under the conformal group. Now, to make our lives easier, you can consider a D+2 dimensional space, a space which is 2 dimensions higher. Okay, imagine that you are in some D+2 dimensional space. Now, for that space, I'm going to set J, nu. So now the indices nu and nu go from 0 up to D minus 1. So define J mu nu to be equal to the generators of Lorentz transformations of the D-dimensional space. And I still need to specify indices for one of the components being, one of the indices being equal to D, right? So nu and nu here go from 0 up to D minus 1. I need to specify the components. If I take the second index to be D, so I want to call this 1/2 K mu minus P mu. I want to write the component nu D plus 1, which is 1/2 K mu plus P mu. And the only thing that I'm missing, if J is an antisymmetric tensor, is the D plus 1 D component, which is equal to the dilatation operator. Okay, so if we agree that this J is an antisymmetric object in its indices, then I have fully specified what this antisymmetric object is. Okay, I have defined something. Now, the nice thing about this object is that if you compute the commutators in D plus 2 dimensions, what you find is something very interesting. So you will discover another object, G, which is just a bunch of numbers, J A D minus G A C, J B D minus G B D, J A C plus G A D, J B C, okay? Now, these are exactly the commutators that you would have. And also what you find is that GAB is the diagonal matrix with a couple of minuses and then all plus, plus, plus. Okay, so you have a couple of minuses here and another D pluses. So if you just look at that, then you can conclude that the conformal group in D dimensions is equivalent to the Lorentz group in 2 plus d dimensions. Okay, so SO2, comma D. Okay, so that's very useful, especially if what I have in mind is to realize this symmetry geometrically. I want to realize this symmetry as an isometry of a space. Okay? Now, I don't want to talk about ADS yet. I want to stay a little bit more with field theory. And I want to have a discussion on conserved quantities, or sources and conservation laws in field theory. Okay? Why do I want to do this? Well, I talked to you about electric current, the heat current, and from the CFT point of view, or from the QFT point of view, all I know is the stress tensor and probably the electric current. So what is this heat current thing? Okay? So I want to define some quantity, some operator, which I want to study in the UV CFT, and do stuff with it. Okay? Any questions? Yes.
Thank you. Okay. It's about the special conformal transformations in CFT. So in the critical point, the theory is scale invariant. And then what is the condition for it to also be invariant under the special?
Well, I'm not sure there is a clear answer to that, to be honest. I think there is a conjecture around which says that you will get it.
Yeah.
If you have relativistic symmetry, unitarity, and Z equals 1 symmetry, you will just get special conformal transformations.
Yeah. There's not any example where this doesn't happen, like in interesting physical systems.
Friends of mine that do conformal field theories have a doubt about this conjecture.
Okay.
And there might be examples, and I should probably look into that. But I think there is.
Okay. Thank you.
I think there is. Yes, you can formally take dilatations, close the algebra, but is what you will get in the end the symmetry of the theory? I mean, is it a symmetry of the theory? You can close a group. I can define any group I like, but is it a symmetry of the theory? Okay. Let's talk about sources and conservation laws. Okay. So now suppose I will say CFT, but it's not about the CFT really, it's about any QFT. So suppose that your CFT is defined on some manifold with metric G mu nu. And it is deformed by some vector operator j mu and some scalar operator O phi. Okay, so when you see this metric here, this stuff, it's not dynamical. We are not doing gravity now. Okay, I'm just taking a QFT, I'm just putting it on a curved manifold. Okay, this G mu nu is not dynamical. It has nothing to do with holography yet. Okay, so let's do all this stuff to our poor CFT. Then you can define the partition function as a functional of your background metric G mu nu, the source for the vector j mu, and the source for the scalar operator O phi. Okay, let's say that you have some action. You can do some path integral if you have a local action. And then the action is a functional of these background fields. Okay, now I want to take this partition function and I want to vary it with respect to the sources. Okay, so I will take minus I, and then I will divide by z, and then I will just have the variation of z. Now, if I, yes?
But can you define what we mean by a theory being deformed by two operators?
Right. So you can, where should I do this? If you have an action for a theory, you know how to covariantize the derivatives and everything.
Mm-hmm.
You can know how to write it on a general manifold.
Yeah.
This is what I mean by this background G mu nu.
Yeah, that's okay.
That's
I was asking about what do we mean by deforming a CFT by J mu and O? What does?
Okay, the G mu nu part is
fine.
what I just said. Good.
Yeah,
We have that.
Okay.
So let me then write two terms. So this is the G mu nu part. And then I can take the J mu and couple it to A mu, and also the O phi, and multiply it by phi s. I just mean these couplings. Okay?
So, but is there a notion of deformation without having, like many CFTs, we don't have a Lagrangian description, right?
Right.
So in that case, what would this deformation mean? Means, are we just adding these two extra operators in our list of primaries or something like that?
Right. Yeah, you would have to deform the algebra, basically. I don't even need this part, right? So if I have a notion of this, then I can start taking derivatives with respect to the sources and compute expectation values of operators. So what I'm going to say does not rely too much on this.
Yeah, but what's not clear to me is that if we just know the partition function of some theory, and then we are saying we want to deform that theory, and we don't know what the form of the partition function is.
Oh, then you don't. Well, but if you know that your theory is I haven't reached the point of invariance yet.
Okay.
But if you know that your partition function is invariant under certain deformations, I mean under certain transformations of the sources, then you will have some word identities.
Okay, maybe I'll wait and
Okay.
ask maybe.
Okay. So if I vary this in general with respect to the sources, then what I will get is an integral root minus g. So the variation with respect to the scalar source is going to give me just the expectation value of delta s with respect to delta phi s, and then delta phi s plus the expectation value of the variation of s with respect to the source a nu times delta a nu plus the variation with respect to the background metric will give me the stress tensor, the expectation value of the stress tensor times delta g nu nu. Okay, so if I keep going, I can write this as an integral. That will be the expectation value of the operator phi times delta phi s. That will be the expectation value of this vector j mu times delta a mu plus 1/2 times the expectation value of the stress tensor times delta g nu nu. Now, this is for a general variation. I mean, I'm varying my sources. I'm taking derivatives with my sources. And I know that I can read off the vacuum expectation values of O phi, j, and the stress tensor. Now, suppose that the partition function z is invariant under gauge transformations of the external field, of the external source A mu. Right, so A mu is just some fixed field. There is no dynamics about it. I'm not integrating over A mu. However, if the partition function is invariant under gauge transformations of A mu, this means that I am invariant under shifts like this, where lambda is some function. Then if I choose a variation here, if I can choose a variation in delta z so that delta g mu nu is 0, delta a mu is just partial mu of some scalar function, and delta phi s is just 0. In other words, if I choose the variation to be just a gauge transformation, invariance is telling me that this delta z should be 0. Okay? So this is telling me that minus I z delta z should be integral over all space-time. And then I will have only the expectation value of j mu, and then partial mu lambda. And that should be equal to 0 for any lambda, for any smooth lambda. However, this is telling me that if I do an integration by parts and nothing goes wrong, times lambda. So this is equal to 0. And since this is happening for any lambda, then this is giving me a conservation law for this operator J mu. Okay? Now, that's a nice thing. That's a word identity that I can write if the partition function is invariant under external gauge transformations. This is telling me that there is a conserved current in the system. Okay? Conversely, if you have a conserved current in the system, you know that you will have, you know that you can couple your current to external sources, and then you will get effectively gauge invariance. Now, the other thing that I want to talk to you about is coordinate transformations or diffeomorphism invariance. So suppose that Z is invariant under coordinate transformations. Okay? And then I can choose a variation for the delta G, delta A, and delta phi S, which is generated by a coordinate transformation. So I'm taking x mu to some x mu plus xi nu, and this is a function of this x nu. So effectively, delta G mu nu will be the lead derivative along the vector xi of G mu nu. The variation of the external gauge field will be the lead derivative with respect to xi of A mu, and the variation of phi s will be the lead derivative along xi of the source phi s. Now, there is a yes? Yes? Over here? Ah, yes. For a vector, any vector, no problem. I want to write it. I like it. I think it's useful for everyone. Thanks. Right. I'm not going to write what this is. There is an exercise problem for you. Okay? So if your partition function is invariant under such transformations, then you can show, and you will show it, I hope. What you can show is that you have what is called a conservation of the stress tensor, although, I mean, it's a word identity for the stress tensor. And this F nu mu, or F mu nu, is the field strength of the external field, the external field A mu. The nu phi s, okay? Okay, I think I should probably stop here. We will pick it up from this point at 2:30, I think. Yes, good. So, thank you. Thank you.